Okay, good morning, everybody. It's 9 o'clock, so it's time to rock and roll. I'm afraid I will not be able to do such great introductions as Eva did. So it was my mistake to allow her to go first. Excuse me, we have already started. Could you please be quiet? And it is my great honor and pleasure to introduce my friend and colleague from the University of Warsaw, Agnieszka Świerczewska-Gwiazda. It's really not so easy to introduce, to say something about someone whom you just know as a friend, not as a research collaborator. But let me say that she's a major contributor in the field of partial differential equations, recipient of numerous research grants, organizers of numerous conferences, and very important in Poland. Recently, just very recently, she was awarded the title of full professor by the President of Poland. So that is, yes, Agnieszka, good for you. We are very happy. Yes. So now she'll speak to you as a full professor. We are very happy about it. And I guess without any further ado, we are all ears. Agnieszka, the floor is yours. Take it away.
Thank you very much for this nice introduction, and of course, thank to Piotr and Eva for this kind invitation. It's a pleasure. It's a pleasure to be here with you and have an opportunity to present some part of mathematics. Maybe if I'm lucky, I will manage to convince some of the young people to choose this direction. Well, I think the task at the beginning might seem not easy because I want to talk to you about partial differential equations, and in particular about some nonlinear systems. So such a thing that you would even not meet if you attend the basic PDE course. PDE is for partial differential equations interpretation. So, but anyway, don't worry if because I know in the audience there are also some younger students, but also some for whom everything might be clear and easy. Anyway, I will try to make my lecture accessible to everyone. So don't worry at all if you have never in your life seen a single PDE, because my point is not to present any technical difficulties really, but I would like to show you how much fun you can have in fact working in this area. I will be talking about Euler systems, which is the system arising from fluid mechanics, and for me, in fact, choosing this direction in my research, choosing this part of PDEs was quite natural because. Well, I've always been interested in analysis, so that was for me sure that analysis is my way to go, and also I wanted to do something that is somehow related with the environment around me. So to describe something that you can see around you and feel it and so on. But there was one thing that I haven't really realized, but a couple of years ago, at good times when we're able to travel normally, we've been on a conference in Baltimore in US, and we had a lunch with our colleague, Professor Chen from University of Oxford, and one thing that he told us, and it's really true. So he said, well, we are so lucky to work in PDEs now, in such a system, in fluid mechanics, in hyperbolic conservation laws, because nowadays there is so much happening now in this topic. There are so many new discoveries. And we can feel like a part of this. and yeah, and he was right. That's the beautiful thing about it, that we do not only talk about the results from 100 years ago, or even from 50 years ago. No, what is around us, these results are from 10 years ago, from 5 years ago, and you really have a feeling that working hard, having good ideas, you can somehow contribute to some change in mathematics that is going on. Okay, so to change. Okay. Okay, so I told you about things from 5 or 10 years ago, but I will start with Euler.
So that's what you mean by recent mathematics.
Okay, so that's where the story starts, and well, in fact, it's even more fascinating that we are not talking about problems that are solved now, the problems that like appeared, new systems that appeared 20 years ago, but we are talking about the systems which have been known for 250 years. So I'm sure everyone in this room heard about Euler, the Swiss mathematician from the 18th century. Well, surely the greatest of the 18th century, but also one of the greatest in the whole time. So we could, of course, you cannot get any picture, well, the photo of Euler, but there are lots of paintings that you can find in the internet. So that's one of them. So let me maybe cite here Simon Laplace, the French mathematician, also probably well known to everyone. At least somewhere you heard about Laplace operator, Laplace equation, yeah. So what did he say? He said, read Euler. He is the master of us all. Okay, so let's agree with that, and see. I want to show you the first page of the paper. It is the paper from 1757, written by Euler, and this is where the equations of the Euler equations were formulated. So the interesting thing is these are one of the first partial differential equations that were really written down. So well, maybe I will not encourage you to read the whole paper. It might be quite difficult, and well, the style has writing has changed a little bit. But I will provide you with the summary of that. So what we have here, I put the Euler system. This is the system of these two equations. The first one is conservation of momentum, and the other is conservation of mass. So so maybe let's start from the beginning. We have two unknowns. This is the velocity field u. So it's if we talk about situation in 3 dimensions, then this will be the vector, and a scalar function p that stands for the pressure. So in fact, if we are in 3 dimensions, the first equation that we see, it's in fact 3 equations, and the scalar and the equation for divergence of u is equal to 0. So let me for a moment concentrate to tell you about the symbols that we have on the slide. But again, even if you see some of them for the first time, don't worry, because what I will be telling about will be mostly ideas, not the details. But anyway, still I want to explain everything, so that you are, if you want, that you are able to follow. So firstly, this stands for the time derivative, because we described these quantities, the velocity and the pressure at each t moment in time and x moment in space, point in space. So with this symbol here, we mean the partial derivative of u with respect to time, and this u cross u, this is the matrix which has the entries ui, uj, the product ui, uj. Ui, uj are the components of the vector u. Then firstly, let's go to the second equation, where we have divergence of u, so divergence of the vector. This operator is defined here. Yeah? So n here for the moment stands for the dimension. Well, the term appearing here is divergence of the matrix. So when we write the divergence of the matrix, we in fact mean divergence of column vectors. So this definition applied to the columns. So these are the entries of this matrix. So divergence of u times u is finally a vector. Okay, so to derive these equations, we in fact are using. Is it? I'm speaking to not loud enough.
No, it's great. I just wanted to take microphone. Could you explain me? I don't understand why this is conservation of momentum. I understand mathematics. Okay.
Okay. So that's the you derive these equations from the physical law, and that's quite an issue. Well, we in fact yesterday morning spent during our lectures like something like an hour to derive the Euler systems from the conservation of mass and conservation of this comes from Newton's law.
It will be more visible that this is a conservation of moment if you put also rho here, because this is a fluid with constant density, and because of this, in fact, the momentum is just equal to up to some proportion up to just u, because this is rho times u is a momentum. And because here the assumption is that density is equal to 1, then rho is not
visible.
Density is not coming. Okay, just explain this, because I think this is Eva question is mostly to this. Why the equation only for velocity is the equation for momentum, but this is because this is a particular case of constant density, where you are just assuming to density to be equal to 1.
Okay, so momentum is proportional to
velocity.
To velocity.
Yes,
to
momentum is proportional to velocity. And in fact, this is equation on the velocity, but because this is proportional to with constant 1 to momentum.
Okay.
Yes, and the second law will so somehow.
Okay, this I understand.
Yes.
I understand.
Okay. Sorry for
Okay. Okay, so that's what is on the slides, but I indeed haven't told it, that the density of the fluid, well, it's constant, and indeed we treat it as one. We could divide this. And so the fluid is incompressible, has constant density, and it describes the inviscid flow. inviscid flow. So it means that the viscosity of the fluid is equal to 0. So we don't have this internal friction, or don't have or neglect it.
Like a good synthetic oil in your engine in your car. No viscosity.
Yeah. Okay. What would happen if we include the viscosity? I will also mention later, because this is the situation in fact which is mathematically easier for us. Okay. So some things that we can observe about solutions for Euler system. So I wrote the first sentence. Assume there exists a classical solution to, and the equations we already recognized them, to Euler equations. So let me concentrate for the moment on this word classical solutions. Because in many cases, when we deal with partial differential equations, well, at the beginning of the standard course at your studies, there are a couple of equations that you indeed solve. So you are able to give an exact solution. But, and well, the solution you give, that it classical, it means that if we have some derivatives in the equations, then this solution is of appropriate class, that all the terms have meaning. And that's what we mean by classical solution. Anyway, in case of particularly nonlinear PDEs, but also many linear PDEs, it's not possible to solve the equation, meaning that to give you, Piotr asked me for the formula and I can give him the formula. No, it's not like that. But still, then people, when saying I solved some problem, it means that I showed existence of solutions. I showed existence of solutions, and usually this existence is not the only step, because what we have in mind is more like well-posedness of the problem. So we want to show the solution, but we also want to know that this is unique solution. So when we start with some initial data, we will end up with unique one solution, not have many of them. And the other properties that would be interesting for us are stability of solution to with respect to the initial data. And this is particularly important when we have some systems from physics or biology, well, when we would like to refer to some experiments which are not always precise. So we want to feel sure that some small impreciseness in the measurements, in the initial data that we give to the system, will cause also small imprecisement in the solutions. Okay, but anyway, sometimes even if you do not know whether you have classical solution, you are checking what would happen if I knew that this classical solution exists. So I will always check what would happen if this was the case of Euler, if this classical solution exists. Let's look at this balance equation. So I mean this balance of momentum, and I will multiply with the velocity. So what happens? I will get such a formula. So you are not surprised in the last term, because this is here the gradient p multiplied with u. Here nothing surprising happens. And here with this term, with time derivative, I multiply it with u. So time derivative of u times u. This is 1/2 of the time derivative of the square. This is the chain rule. So that's easy. And And what, well, this term changed here, the one from here to here, and I will show you this computations. No, this is wrong direction.
By multiplying,
yes.
Taking the scalar product. Right?
Yes, yes.
And this integration of a t, what is the t?
Well, u depends on t and x. So you describe
capital T, letter T.
Ah, okay. Here.
Yes.
You are going forward. I didn't. I will tell you in a moment. But that's just Taurus.
Taurus. Okay. Good.
I should press the right button to go the right direction, and sometimes I'm losing. Anyway, so for the moment, take a look at this term divergence u times u, and I multiplied it with u. And okay, to believe me that you really write it in this way that I put here. You can just write it in the component way. So what is here? I'm just using the definition that you saw from on this first slide where the Euler equations appeared. Okay, so this derivative of the product, yes, and then I put it together like that, and this is why what is here corresponds to the second term, and that's fine because the first term vanishes, and this is because the divergence of u is equal to 0, and divergence of u, let me remind you, this is exactly what is here in this bracket. So that's why after multiplying with this term, with the equation with u, from this term I obtain the one here. Okay, and the next thing that I will do is I will integrate the last equality. Well, I wrote it over Taurus because I want just for the simplicity to have less things to explain. I consider here that periodic case, so we don't have to worry about any boundary terms, but okay, we could also work in the whole space, and in fact also in the bounded domain. Then we will need some boundary conditions, but I don't want to go into
this is an n-dimensional Taurus.
Yes. Okay, so
What? No, is that over x, integrations over x and x.
Yes, and dimensional. Okay, so what happens? Let me first take a look at the last term, because while integrating by parts, the gradient of p will end up as a divergence of u times p, and the divergence of u is don't forget, this is 0. So in that way we get rid of the last term. Then the middle term, there was a purpose that I wanted to rewrite this in that way, because now again integrating by parts, this gradient will end up as a divergence of u, and again thanks to this condition I get rid of the term, so I'm only left with the first term here, and what I get is the condition here that the derivative with respect to t of this integral is equal to 0, and what we recognize here is the kinetic energy. So consequently, if we integrate this in time, we can see that this kinetic energy is constant. Yes, what we have at the initial time t equals 0 will be the same, will be conserved for all times. Okay, so this I had. Okay, so I think I explained here. Good. So anyway, the issue of conservation of energy. This will be something that will I will come back to this, and this will be quite crucial in further talk. I want to mention also about another system, Navier-Stokes system. So, well, it's similar. You can recognize once you know Euler system. So you see the difference is that we have here the Laplacian term. So it's the second order operator, which refers to viscosity. Here the effect of this internal friction. The system was written later by Navier, the French engineer and physicist, and later also contributed by Stokes, the Irish physicist and mathematician. And well, there are two reasons why I'm mentioning the Navier-Stokes system. So one thing is that such a basic strategy when you work with partial differential equations, and you have some equation that you don't know how to solve, then you take another equation that is kind of similar to your equation, and you solve the one that you know how to solve, and you treat it as some approximate system for your original system, and then you pass to the limit with, let's say, with some parameter, or you can have different strategies when choosing the system that you know how to solve. Either you can add some term, which then gives you the better properties of the system, or you can project your problem on some finite dimensional space, and then you end up with finite dimensional system, and you pass with the dimension to infinity. Well, there are various strategies, but anyway, such a basic one is to construct some approximate problem. So believe it or not, but anyway, the Navier-Stokes system is easier for us to handle than Euler system. So what we could consider is the Navier treating the Navier-Stokes equations as the limit, as the approximate problem to Euler equations, and take this parameter nu here that stands next to viscosity, and then pass with nu to 0. And we would like to expect that the solutions of these approximate problems to Navier-Stokes will, in the limit, give us the solution for the Euler system. Well, unfortunately, this is wishful thinking. It this limit passage doesn't work. I don't want to go into details, but not in this case. But anyway, the second reason is why I want to mention you the Navier-Stokes equations. Well, that's the second issue is that maybe anyone needs some money, and one way to get some money is working on Navier-Stokes equations. Anyway, that's a huge issue about singularities in finite time of these problems, of Euler problem, of Navier-Stokes problem. And in fact, in the year 2000, the Clay Institute of Mathematics at Oxford, they listed 7 problems that they find particularly difficult. And as well, they are called Millennium Problems. You might have heard, you probably have heard about it. And anyway, well, solving these problems, you get the award of $1 million.
It was announced in Paris. Congress.
Yes, yes. So having Navier-Stokes equation here, having it on the list. So what is known? Existence of global in time solutions. Well, in fact, weak solutions. I will come to the notion of weak solutions in a moment. This is something that the result that comes from the 30s. But anyway, the questions of uniqueness of solutions, which is very much related with the question of regularity of solutions, these are the problems that are still open. And well, of course, not everyone who works and solves difficult problems is then interested in this money, which is in fact the case with Poincaré conjecture, which was solved by Grigori Perelman, who reject to accept the award. So
don't make this mistake.
yeah. Well, that's what he said. I can. Well, I'm not interested in money or fame. I don't want to be on display like an animal in a zoo. And yeah, that's in fact, this is not the only award that he received and reject to accept. The same issue was with Fields Medal. Fields Medal, as you know, there are no Nobel awards for mathematicians.
There is Howard.
Yeah, that's I'm aiming to say that the awards that mathematicians can get are, well, Abel Prize, very prestigious prize given by the King of Norway, and also and another award is Fields Medal, which is given every 4 years to mathematicians under 40. So anyway, Perelman didn't accept neither this prize for solving Poincaré conjecture, neither nor Fields Medal. Okay, but yeah, we are interested in Euler. Forget the Navier-Stokes equations. And let me summarize what is known in this topic. One question: I should make a break somewhere in the middle. Yes.
Yes, I mean,
but I can choose it.
Yeah, you can choose the time.
Okay. Good. What do we know about solutions to Euler system? So there are results from 20s, which state about local in time existence of classical solutions. Local in time, that we know that there exists after certain time. And we would like of course have global existence. So there's another thing that I want to mention is global existence of solutions that you would usually can meet in the literature the name for Udovich solutions. And Udovich solutions, or this goes together with vorticity, the notion of vorticity equation, but what is quite often somehow being forgotten are the result of Witold Wolibner, and I'm mentioning it since there are lots of students from Wrocław here, and Wolibner spent a huge part of his life after Second World War in Wrocław. However, the results that I recall here from 1933 these are the results from the time of his stay in Warsaw before the war. So, but anyway, whenever you hear about Udovich solution, have in mind that the results of Witold Foligner are important here in this. In the moment, there's also about that such a nice overview paper in the journal Wiadomości Matematyczne. I recommend you. I recommend it for reading in some free moment. It's nice. I will spend 2 slides to tell you about this vorticity formulation, that you have an idea. But anyway, still, the global in time existence of solutions in any space dimension, that's an issue. I will tell you, because there are important things that happen here, but let me first build some suspension. Okay, so 2 slides about this Udovich solutions and vorticity formulation. Okay, you cannot see the whole screen because it is in 2D case, which is here in looking at this from the point of view of the results that we can have. The 2D case is more interesting than 3D case, and let me tell you why. We stop looking at the fluid as for the description for the velocity and pressure, but we look at the curl of the velocity. So when we apply the curl operator to the equation, I don't want to go into detail, so I don't want to go into computations. But believe it that you're getting rid of the pressure term because you have the rotation of the gradient, so this is 0, and you end up with the equations, such equation for the quantity omega, and this omega is the vorticity. Of course, you can have still u here, but you can write u in terms of this omega, of this vorticity. That's here is potential, but anyway, once you know how to solve Laplace equation, then you can find the formula of u in the words of omega. So what you end up here is in fact kind of transport equation, and transport equation is something what we like because in transport equation we know that there are some quantities that are transported, that are conserved. We feel comfortable when we work with transport equations. So in this case of in two-dimensional case, in fact, it's possible to show existence of global solutions, classical solutions. So that's nice. Short remark here about the energy.
Question: is the heat equation a transport equation?
No, the transport equation, the heat equation is the second order equation.
Okay.
And this is transport equation, the first order equation.
Yes, but
sorry,
derivatives. That's right.
Yeah, but for the moment you forget it.
Okay.
Yes, okay. Yes, you treat this here. Omega is my unknown. Yeah. I still cannot catch the direction I should go. Okay, why two-dimensional case is easier than three-dimensional case? That's the problem is when you apply curl to the equation, then in 3D you would get also such a term. Well, you could say like vortex stretching term, and then, well, you do not have such a homogeneous transport equations, and you do not benefit from what you would you would in two-dimensional case. Okay, again. Okay, so when we cannot show existence of classical solution, this is the moment where we should start to think, what is the right concept of solutions? Maybe I can define the solutions somehow differently, and in define the class of solutions, and in this class maybe I'm able to show well-posedness of the problem. Does it make sense to consider solutions that are not continuous? Well, it does, because when you think about conservation laws, then it's natural that you have solutions that in physics that are not continuous, like when you have a shock wave. Yes, it's discontinuous solution. So so we can get the well-posedness of the problem if we somehow relax the notion, or let's say generalize. I will call it weak solution. Well, not only I did it. In general, this is the notion that is well, the fundamental notion in the modern theory of partial differential equations. And as you will see in a moment, when I define the weak solutions to Euler system, they are in the formulated with help of some integral identities. And this is in fact this is quite natural. We shouldn't be afraid of this. This is some abstract mathematical object, because when we derive conservation, this equations coming from physical laws, they come from the integral formulation. Yes? So in fact we feel comfortable about it. Okay. So once more, I repeat the Euler system in this classical formulation. So these two equations, and with some initial conditions. So we say that for t equal to 0, we have some given function u0 of x. I recalled you this formulation because I want to pass to the weak formulation. Let me see how. Okay. So maybe first let's take a look at this integral identity. More or less, what's happening? You can think like looking at these equations, multiplying it with some test function. Test function is a function that is smooth and have compact support, and then integrate with respect to time, time and space. So how can we benefit from this action? Well, the point is that we can integrate by parts, so we can put derivatives on the test function. So what happened? And well, the test function, remember, this is smooth. So it can take any derivatives that we give. So then to have the terms, in fact, well defined, we do not need to require anymore that solution is differentiable. So this divergence from here ended up as the gradient here, and this time derivative. And when integrating by parts with respect to time, here I also got this term related with the initial condition, because I was integrating from 0 to infinity.
So I'm confused. What is the meaning of a column after you SOU? Yeah.
Okay, this is like scalar product between matrices. because now you can also put a dot here. So it's not crucial because you had divergence of the matrix, which was a vector, yes, and now it is a matrix. So, okay, well, D here in my notation is what was N before, so D and N is. I work hard to unify, and that U is always U, not sometimes V, but I haven't managed with the dimensions. So.
Well, it shows that solutions are not always block.
Yeah. Anyway, so when speaking about weak solutions, so one thing is from the momentum equation, and also this condition divergence U equals 0 is still we require it. Well, of course, we have in mind also in this weak sense, or in other words, distributional sense. So it does mean that really the first derivatives of U need to exist. That's again like multiplying with the test function. When speaking about the weak solutions, also it's not only this integral identity that we require that holds for every test function, but also we prescribe somehow the regularity of solutions. So here it is L2 log. So it is square integrable in space and time. Okay. So again, the wrong direction. And I concentrated a lot on the conservation of energy. So what are the problems of weak solutions? Well, these computations that I showed you for classical solutions may fail to be true for weak solutions, because this chain rule that we had, it may not be valid. So so we cannot justify that this identity hold. So that's the question. That's the question that is interesting for us, and maybe that's some idea to stop after this slide and to have a break now. And when we come back, we'll try to understand whether weak solutions conserve the energy and or when they do not.
So maybe there are some questions right now. So grab a mic and ask. No questions? Any questions from the internet, Zoom people?
Yes, sir. What's the motivation to take the test function in the solution? In the previous slide. Here you have taken the test function psi x, right?
Yes.
So what's the motivation to get it? Means how do you get like we need this? What's the reason?
You mean in the divergence equation or the?
Yeah, in the divergence equation. Yes.
Well, I wanted to underline that it's in the what you mean is that usually when you see the definition of weak solutions to incompressible Euler, it finishes here, yes, and in fact everyone knows that solutions are divergence free, or in other words solenoidal. But since I want to make clear to all the people who. For those who it will not be obvious that this divergence is meant in the distributional sense. So that's why I wrote it here. So because as you see, well, the divergence was integrated by parts. So to make clear, particularly to the students, that solutions does not need to be C1 with respect to space.
Thank you.
Okay, are you happy?
Yes, sir. Yes, sir.
Any further questions? Please fire at will. There's no problem. We have time. Okay. Since there are no further questions at this stage, I have a question. This omega is integrate over. This is what some compact subset of. At the last slide where we paused, we have integration over omega. I know I'm asking boring questions about.
Yeah, but what?
Your last slide at which you stopped.
Ah, okay,
Yes.
okay. This is the domain. So omega can be.
Is it compact? Is it...
So either omega is an open set, or it can be torus, or it can be the whole space, some domain. I don't want to get into details.
Okay.
For the moment, yeah.
Okay.
So sorry, it's not consistent with the previous one.
Okay, good. So let's have a quick break and resume 5:10. Muszę teraz zastopować. Nie zastopować, tylko spauzować. Pause recording. Recording in progress, talk in progress. Agnieszka, it's all yours again.
Okay, thank you. So again, wrong direction. So conservation of energy, that will be the main issue now after the break. So I want to mention Lars Onsager, American physical chemist and theoretical physicist. Also awarded by Nobel Prize in chemistry. And why are we mentioning him? So the point is that in 1949, he formulated some hypotheses. As you may expect, he didn't prove it. He just wrote it. I recall it. That's why this slide looks so awful. But let's go for it. It is of some interest to know that in principle, turbulent dissipation could take place just as really without the final assistance by viscosity. So we are speaking about Euler system. In the absence of viscosity, the standard proof of the conservation of energy does not apply, because the velocity field does not remain differentiable. Okay, that's we already understood. Yeah? In fact, it is possible to show that the velocity field in such an ideal turbulence cannot obey any Lipschitz condition of the form. So here's the condition. Well, he calls it Lipschitz, but we okay. This n here is not the dimension. This is exponent. But I wanted to keep the original notation of Onsager. So what you see is, in fact, we call it Helder continuity. Yes, you divide it by r to power n, and this is bounded. For any order n greater than 1/3, otherwise the energy is conserved. Of course, under the circumstances, the ordinary formulation of the laws of motion in terms of differential equations becomes inadequate and must be replaced by a more general description. So what I can tell you? Well, I can in fact tell you, be careful, because we are approaching turbulence.
Sorry, may I have a question?
Yes.
So this exponent is the dimension.
Yes. In a moment, I will put it in more readable form. I was recalling some Heisenberg saying, when I meet God, I'm going to ask him two questions. Why relativity? And why turbulence? And I really believe he will have an answer for the first. So yeah, really the turbulence is a difficult issue, let's say. But let me come back to this conjecture of Onsager, and I want to put it in more concise way. So let U be a weak solution to incompressible Euler system, and he claims that if U is a Helder continuous function, is in C alpha, with alpha larger than 1/3, then the energy is conserved.
So alpha and n.
Yes, alpha and n are the same. Yes, I switch now to alpha. I left on
That's not an integer, right?
Yes. It's not an integer, so I don't want to. I recall it was an Onsager's statement, but we are so used to that Helder functions are C alpha, so let's stay with that. And if for any alpha smaller than 1/3, there exists a weak solution which does not conserve the energy. Okay, so that's an interesting issue with these solutions that do not conserve the energy. If we try to imagine them, well, here we can go to 90s, and there's a result of Scheffer, who tells us that there exists a weak solution. It is two-dimensional result. The weak solution, which is square integrable L2 over time and space, to Euler system with a compact support in space and time. Can you imagine such a solution? So maybe let's make an experiment. Okay, I will pour some water into the glass, and now I will ask you to close your eyes for 3 seconds. But everyone, please do not cheat. 3 seconds. Close your eyes. 1, 2, 3. Okay. Was there anyone who was cheating? Okay, good. So I will tell you what has happened during these 3 seconds. This water from the glass went out, then went to that wall, then to the ceiling, then to the end, came back, and came back to this glass. Do you believe me? but this is a great example of the solutions which is compact support in time and space. This is zero velocity at the beginning and zero velocity at the end, and suddenly the energy was created and then dissipated, and yeah, that's okay. Well, I saw Piotr didn't close the eyes, so I should admit that I was lying because otherwise Piotr will tell you that. So yeah. So let's. Okay. Well, what's so these are surely such a non-physical solutions, and such examples are constructed. Scheffer and Schneermann. What else we see from that? Because think about Euler system. Okay, you probably remember this. And if we start with initial data velocity equal to 0, so can anyone find something that will also be a solution? Something simple. 0 initial data. So I will help you. The solution that's constantly equal to 0. This is a good solution. So this is the mu equals 0. So this is also a solution. Okay. So this solution is constructed by Scheffer, and this is what we by ourselves can find this trivial solution. It shows the non-uniqueness of the problem. Yeah. So we see that there is some we are lacking this uniqueness. Well, the proof of Scheffer is quite difficult to read. It's long, complicated, and you cannot really don't really know whether solution is an element of the energy space. So it is an infinity too. Then in 1907 there was a simpler proof of Schneermann, also in two-dimensional case, but also quite complicated. So okay. So we know there is a problem with weak solutions, that they are not unique, but their situation is even worse, because in 2009, two mathematicians, Camilo Delelis and Laszlo Szekelyhidi, they found some initial data for which they were able to construct solutions to Euler system with compact support in any space dimension larger than 1. And these solutions were okay. And there were infinitely many of these solutions, not one or two, but infinitely many. Well, these solutions were L infinity times L1, so they are bounded and integrable. It was a step towards Onsager's conjecture that you could find solutions that dissipate energy, but anyway, but still, these were not regular solutions in the sense Helder regular with exponent smaller than 1/3. But anyway, the point is that the proof is different to what I told you. Typical scheme for PDEs: take an approximate system, solve approximate, pass to the limit, have uniform bounds, pass to the limit, use Banach-Haloglu theorem, and so on. No, it's very elegant. It uses different methods. It takes some benefit, the big benefit from the methods of differential geometry. The method is called convex integration method, and I will very briefly present you what's the idea behind that, but really without details. So what else can we have from convex integration? Well, as in the results of Delelis and Szekelyhidi, they showed that you can find solutions that initial data and sort of the, but another result of Emil Wiedemann is for every solenoid, so divergence to initial data, there exist infinitely many weak solutions to Euler system. So we are lucky because Emil is here. So one would be happy to celebrate that the problem of global existence is solved. Does it lead to the well-posedness? Well, unfortunately not, because this comes together with this non-uniqueness, and so this gives us this comes with an issue of ill-posedness of the system together in the context of weak solutions. And let's try to catch a little bit of the idea why this what happens there, why this non-uniqueness, and what's the concept behind that. Well, John Nash, so another fantastic mathematician. In fact, the only one to get the Nobel Prize in economics and also Abel Prize.
Wait, I mean, now Roger Penrose got the Nobel Prize, so at least two mathematics.
Okay.
Abel and Nobel,
So Nash in 2015 obtained the Abel Prize, and it was very unlucky for him. It appeared to be very unlucky for him because together with his wife, coming back from the airport, they landed from Norway in Newark, and then going by taxi to their home, they had a car accident and they died. So that's this story finished very, very sadly. Anyway, but he got the Abel Prize for his contributions in partial differential equations. And another citation of Gromov. Nash was solving classical mathematical problems, difficult problems, something that nobody else was able to do, not even to imagine how to do it. But what Nash discovered in the course of his construction of isometric embeddings is far from classical. It is something that brings about a dramatic alteration of our understanding of the basic logic of analysis and differential geometry. Judging from the classical perspective, what Nash has achieved in his papers is as impossible as the story of his life. His work on isometric immersions opened a new world of mathematics that stretches in front of our eyes, is yet unknown directions and still ways to be explored. So, so just to give you the feeling of that, so the theorem of Nash comes from 1954 with some contribution of Kuiper from the year after, which more or less says that every short embedding of a compact Riemannian manifold can be uniformly approximated by an isometric C1 embedding. Okay, I don't want to get into details to explain you each word that appears here. What I want you to get from that this is quite counterintuitive. So if you
could you tell what is short embedding? Somehow a few words?
Such a mapping that the length of the curves gets shortened. So anyway, the feeling that you should have is if you get the piece of paper and try to make the torus of this, so the ring. So well, the first part goes easily, but the next step that you want to do to bend it and to have to put this end with that.
You can also make blindfold. You can also make blindfold.
But I wanted to do this. So without tearing the paper, yeah, you think that you cannot do it, but you can. But you can, according to Nash theorem, you can. And what is quite interesting, because in 2012 some paper that with the images how you can do it computed numerically, and what I want to underline here are these ways, this perturbation, and that's the issue. Or another thing is that if you want to put it in your pocket, I don't have the women's trousers. Usually don't have pockets, but if someone else wanted to do this, you can imagine that. Is it important?
No, I can bend.
You can bend it, but you could also, according to Nash theorem, you could also do it in a C1 way. So this is of course not, but in principle, you could. So and another citation, in 1954, Nash introduced a concept of non-smooth embeddings, monstrosities that made monstrosities of awful monsters, something more awful than a monster, that made it possible to do impossible things such as crumpling up a ping pong ball without deforming it, or constructing a perfectly flat ring. This is a citation from the book of Cedric Villani, another Fields medalist, and Birth of a Theorem, a Mathematical Adventure. The book was in fact translated also into Polish, and I recommend you reading that because it's really nice. You get kind of such a feeling of mathematical life. So you when you consider, why do I want to do PhD? Do I find myself in academic career? How is it? Well, read the book. It tells you a lot. a couple of years ago. It was translated to Polish also. Okay, okay, I will try to be brief because I how this is related with fluid mechanics. So this is related in a way that you change your Euler system to linear system. So in this place where we had this non-linear term, you put some trace-free matrix U, and you end up with highly undetermined system, but linear, and a non-linear pointwise constraint. And anyway, this idea of Nash is like the starting point for the approach developed by Deleuze and Sakharishvili. So the solution is generated by some iteration scheme. So in fact, you consider sub-solutions which are produced from the previous sub-solution. You add some perturbation, but they had to be so highly oscillating in a way that what you get is still a sub-solutions. And the final iteration scheme is a superposition of infinitely many perturbations, which in fact converge suitably to an exact solution. So, so this notion of the sub-solution here is a key point, and then you can proceed two different ways. Either you can reconstruct the solution, so you know how it looks like, or the other way, you use some abstract facts like Baire category method. Anyway, since the oscillations are introduced in this very non-unique way, then you get so many solutions from the same solution. Okay, wrong direction again. So the summary for this Euler system, again by Villani. Thanks to the Deleuze and Sakharishvili, we now realize that even less is known about Euler's equation than we thought. And what we thought we knew wasn't much to begin with. So the situation, how is it? Oh, sorry, okay, this I will skip. Okay, and summarizing with this Onsager's conjecture, because it was stated exactly. C alpha solutions, alpha smaller than 1/3, alpha larger than 1/3. So this started some kind of a race that people were doing research to find the solutions which are Helder continuous. And well, I mentioned here two results with alpha, you see 1/5, but there were results with alpha 1/10 and 1/7 and so on. And finally, the story is closed. In 2018 and 2019, the two papers, they differed slightly, but the first one was also Philip, I said. But I think it's honest to give credit to both of them, and they solved this negative part of the Onsager's conjecture. Negative. This means about these solutions that dissipate energy, that there exist some solutions which are Helder continuous, which dissipate the energy. Here I have, for any alpha, there exists a weak solution which does not conserve energy. But let's come back for a moment to the positive side of Onsager's conjecture. So I put it in red. So if solutions is C alpha, then it provides that energy is conserved. Okay, so this was the easier part because it was solved in 90s. Well, two papers of Eng and Constant ENT. Well, the second paper was in fact earlier one. However, it was not really stated in exactly in the space C alpha. And the second paper was formulated in the Warsaw spaces. Okay, most of the audience probably doesn't know the notion of Bies of spaces, but doesn't matter anyway. It's also about we control the shifts. Anyway, the result in Bies of spaces gives us the result in Helder spaces. That's the message most important for us, and that's what the in fact how the result looks like. If we have the solution, which is free in time, and here think about C alpha to incompressible Euler system, and this alpha is larger than 1/3, then the energy is conserved. It was considered in periodic case. And one of the approaches how to, in fact, this paper is short. There are 4 pages, and maybe even the last page is empty. I guess, yes. Sorry? L3 is that this is the notation for the so-called Botner spaces, so time dependent. So these are, I mean here the mapping which comes from the time interval 0t to, here's BSO, but let's think, the space of Helder continuous function over space. And this mapping with respect to time is L3. And here the target space is the space of Helder continuous functions with respect to space. This is C alpha, and this is. Yes, this regularity that we have in Onsager's conjecture, this refers to regularity in space.
Is it important when we are here in dimension 3?
No.
And what will happen for alpha exactly equal to 1/3?
Well, you can try to answer this question. Okay, so very shortly, because this paper is short, so very shortly I want to tell you what's the idea, how to deal with such a problem, because I could show you on one slide, in fact, that if U is a classical solution, so then what I can do. And so what I want to do here is take a test function. I want to take the solution, but it's not a good test function because it's not regular enough. So I modify it, and then it's smooth. But I modify it twice, so that one modification I can put on the equation. Okay, so modification commutes with the derivatives, that's fine, but modification does not commute with the nonlinearities of multiplication. So my problem is the term U times U. It's not very strong nonlinearities. Well, one could say, well, nonlinearity for beginners because it's bilinear, which is good, but still it's nonlinear. So what you need to do, so you cannot work with this nice computations that I had on one slide because of this nonlinearity. So what you do, you make some computational tricks. You write it as the term that you would like to have, and that you can show that it vanishes. You write as such a product, of such a shifts, in fact, and the remaining term. So why these shifts here are important? U epsilon, this is U modified, so that's why you need to think about it as shifts. Because knowing about the solution, that it is in Helder space, you are able to control the shifts. So here's the point where this Helder continuity comes into play. And the remaining term, and about the remaining term, you need to work to show that it converges to 0. Here I showed you the estimate that they got for the remaining term. Let's not concentrate too much on that, but we see that there's epsilon to some positive power. So if we go with epsilon to 0, we see that this would be the way to get rid of this remaining term. Okay, so I have still a couple of minutes, and I will try to shortly. Is it the end? Because we have positive part of the Onsager's conjecture, negative part of the Onsager's conjecture. So is there nothing more interesting to do here in this study? No. I want to shortly tell you about maybe let's come back to such thing of flux, another Apple Prize winner. There is no theory for the initial value problem for compressible flows in 2 space dimensions when shocks show up, much less is in 3 space dimensions. This is a scientific scandal and a challenge. This is from the year 2007, and you saw on the slides that 2009 and 2011 and so on, there were results on convex integration. I only mentioned to you that the results for incompressible fluids, but also in the case of compressible fluids, people were trying to show something. There's a huge gap between what you can show for compressible fluids and incompressible, but still, in this last 14 years, still the compressible case it hasn't changed very much. It's still waiting for new results. And what I want to mention is we together with some of our collaborators, Piotr, Emil, and Edward Feyreisel, we wanted to check what happens if you consider compressible Euler systems and see such a Onsager's conjecture, the positive side. Is it really some condition that you put on the solution that would provide you that the energy is conserved? And by compressible Euler, we get additional quantity, which is the density of the fluid. And now the pressure becomes the function, is the function of the density. Okay, this is such a barotropic case, because in general situation, this pressure could be more depend on other factors, and I neglect here any temperature effects.
So that's what Piotr referred to at the beginning.
Yes. Yes. So and as here I thought this linearity was easier. Then here we have real non-linearity. The pressure is the function of this rho. But anyway, we show that analogously as in this incompressible case, we can show that for alpha larger than 1/3, the solutions conserve energy. This alpha is again this exponent in Helder spaces. We also formulated like the other guys in BSO spaces, but you can think about it as the result in Helder spaces. Okay, and so once we manage with this nonlinearity in the pressure, well, then we thought, well, we can deal any nonlinearity, let's say, and in fact, we have noticed that this differentiability exponent with 1/3 is such a recurring condition. So it's not only related to incompressible Euler system, but you can have it even if you formulate your system in a very general way, such a conservation law of the first order. Divergence of some function is equal to 0. G of the U of X is solution. Divergence of G of the solution is equal to 0. So this, I wrote here capital X because this can include our time derivative and space time variable and space variable. So in this general form, we can also have the equation time derivative of U plus divergence of something from something. Yeah, and surprisingly, this 1/3 was coming back to us. What I want to mention here that this 1/3 exponent in the context of Euler equations is often related with Kolmogorov's turbulence theory. So this is maybe you have heard somewhere like about energy cascade and the conditions that you have in the Fourier space, and when you translate this into the physical space, you get also the 1/3. Well, it might be true, of course, but anyway, also the result what you have for general conservation laws, this includes the formation of elastic body, and this 1/3 again. So here we do not speak about turbulence. So maybe the turbulence, this relation of turbulence, well, it's not so clear. I do not claim there's no relation, but yeah, that's a nice question to try to answer about that. Okay, so thank you very much for your attention. I hope you enjoyed.
Agnieszka, thank you very much for the public. Thank you, it was absolutely great. We all enjoyed it. Any further questions? Adam, go ahead.
Yes, so you mentioned that this exponent is the same for each dimension. We formulate the problem in terms of Hilbert regularity, but Hilbert spaces are related to the so-called Sobolev spaces. And how does this problem behave in each dimension if we try to formulate it in terms of Sobolev spaces?
Yeah, well so you can in fact think about Biesov spaces, yeah, but well, still there's no relation between the dimension and the alpha exponent.
So still 1/3 is
Yeah.
What we just exactly say that in fact the Biesov spaces are both generalization of Herder and the Sobolev spaces, because in Sobolev spaces you are just assuming that the derivative is integrable, and in the Biesov spaces this is a generalization of two concepts. Concept of Herder spaces, the shift is bounded simply in supermuon, and in the context of Biesov spaces, the shift is integrable with the proper exponent depending on the size of the shift. And result in the Biesov spaces is both you know, like Sobolev and Herder together. This is a function space which generalizes both concepts. Okay? Like Agnieszka was saying.
I'm happy, Adam.
yes.
Eva, no further questions. Okay, anybody else?
There's
Chat, why don't you open chat? Yeah, click on chat. Thank you for a very interesting talk. Okay, so Zoom folks, do you have any questions? Nope. So in this case, let's thank Agnieszka again for this beautiful talk. And let's try to be on time and begin at 11 a.m. sharp.
Ja się zrobiłam po prostu.
Brawo, ty. Muszę włączyć nagrywanie, bo jeszcze teraz wszystko, co mówimy, się nagrywa. Stop recording.
I am